Welcome to this session about our fascinating Milky Way with Amina Helmi. I will introduce you in a moment. This session is co-organized by Space Society Twente, Arago and Ockham. That's important to mention. I'm very happy that Amina Helmi is our guest this afternoon, that you found time to come from Groningen in your busy schedule to talk to us about the Milky Way. Amina Helmi is a full professor at the Rijksuniversiteit Groningen in the field of dynamics, structure and formation of the Milky Way. She did a groundbreaking PhD shedding new light on the formation of our Milky Way. She discovered the first indications that our Milky Way had merged a long time ago with other galaxies. That's a very exciting discovery, of course. And Amina Helmi is searching these older galaxies. They are some kind of fossils, like you're an astroarchaeologist, so to say. So she looks back in time and tries to find out how our Milky Way came into existence. And it's worth mentioning that one of these rotating star systems, which was merged with our Milky Way, is named after her. It's called the Helmi Stream. And that's really quite an honor if you have a discovery, a very, very big group of stars named after you. So I'm very happy you're here, Amina. Now I want a big hand for Professor Amina Helmi.
Thank you for the very nice introduction. It's a pleasure to be here. It's taken some years to find the right moment, so I'm actually very happy to be here today. And what I want to talk about, or what I want to tell you about, is what we have learned in recent years about the formation of the Milky Way from the satellite that's depicted here, the Gaia mission. That's a European space mission that was launched in 2013 and was scanning the sky until very recently, providing us with a huge amount of information about the galaxy, about how it formed. And from this satellite, there's a great deal that we have learned, and that is what I'm going to focus on today. But before I do that, I wanted to, because this is the week of inspiration, and this is actually one of my favorite pictures, astro pictures, I wanted to spend a few seconds on this picture that shows, the Milky Way in its grandeur, a scene from a site in Chile with a telescope and a dome, with probably an astronomer inside. And what I find so beautiful about this picture is the contrasting scales, right? We have, the universe, we're looking at the universe, and we have an astronomer here trying to figure out how the universe was put together, why the night sky looks the way it does, whether there is life elsewhere in the universe. And that contrast in scales, this building, the universe itself, us, tiny, but still able to grasp and learn about how the universe was put together and why the sky looks like the way it does, as you'll see later today. I find that fascinating and very inspiring, and I thought it would be a nice way of starting this talk. So what we see here is the Milky Way. That whitish band of stars that you see on the sky is made up of, whitish band on the sky is made up of billions of stars that are too far away to be resolved with the naked eye. But if we zoom further, we see, especially if we have space telescopes, we see all of the stars, we see dust and gas. We basically see our galaxy, which is a system that's edge-on. It's like a disk, and we see a band on the sky because we are in that disk, and projected on the sky, it gives you this band of light. In these dark clouds, what we have is new stars forming. With these new stars forming, also planets are forming. So roughly, there's one sun formed per year in our galaxy. So it's an active place of star formation. And whenever there is a star, there's a planet forming at the same time. And in recent years, we've discovered a large amount of planets, and we're still learning a lot about these systems. It's a very young field. The field of galactic astronomy is slightly older, and that it has led us to realize that the Milky Way is just a galaxy like many other galaxies in the universe. As I was saying, it's a disk galaxy, so if you were able to look at the galaxy from outside, if you could place yourself above the Milky Way, then it would probably look like this, with spiral arms, stars, star-forming regions. But we are inside it, so we cannot get this view. We can only try to reconstruct how the galaxy looks like. So it's probably from the outside, if you were to put it edge on, and you would look at it from the outside, it would look more or less like this. So it's a conglomerate of stars, dust, gas, and dark matter that you probably all heard of, that we don't know what it is, that is held together all through the mutual gravitational attraction that all of these bodies feel. There are, as I said, many billions of galaxies in the universe with a large variety of shapes and sizes and brightnesses. But it turns out that of the large galaxies in the universe, about 2/3 of them are disks, like the Milky Way. In terms of the size, the Milky Way is also rather typical. So it's kind of an average galaxy, right? Not too much that's special about the galaxy. And because it's sort of an average galaxy, it can teach us, but we can study it in a lot of detail because we are inside of it. It can teach us a lot to try to understand how galaxies in general form, because it's a typical example. It teaches us about what physical processes take place in galaxies, in the universe, and also, as I was saying, for example, it can teach us about what dark matter is, or at least we can try to chart the dark matter in our galaxy and learn about its properties in that way. But I think the reason many of us are fascinated by the Milky Way is that it's our own galaxy, right? And we're always interested in understanding our own origin, our own home. So one of my drivers, at least for understanding the Milky Way, is understanding the origin of our home in the universe. And that's the focus, actually, of my research, or at least a great deal of my research. So let's zoom in into the Milky Way. So as you can see from this image, the Milky Way has several components. So it has a disk, a thin disk, which is where the majority of the stars in the galaxy are located, right? And that defines the shape that we see on the sky. Stars in the thin disk, as I was saying, are forming continuously at a rate of one sun per year, roughly. And stars in the thin disk are moving in circles around the center of the galaxy. So they're moving in a very orderly fashion around the center of the galaxy. We have an enhancement in the central regions, which is the bar or the bulge, that host, probably you've heard of, a very massive, a supermassive black hole. We have a thick disk, which is slightly thicker than the thin disk. And what's interesting is that the stars in the thick disk, they are moving on less of these circular orbits. They are slightly more elliptical, and they go far above the plane. And then we have the stellar halo, and the stars in the stellar halo can travel very far out, so they form a halo. And what's interesting, so they have very different motions. What's also very different is that the stars in the halo are extremely old. They're basically the oldest stars that we know of, live all in the stellar halo. And so what you begin to see is that the stars in the different components are not only differently distributed in space, they have different motions, but they also have different properties themselves. They were formed at different times. And so if we are interested in understanding the history of the galaxy all the way back as far as we can to the Big Bang, then the place to look at is the stellar halo, because that is where the oldest stars in our galaxy live. Yes, and there's one more thing that maybe I should stress here, which is why we can do this reconstruction of the history of the galaxy, is that we have, as you can see in this picture, we have a wealth of information for individual stars. We can see and measure the properties of individual stars. And we can only do this for the Milky Way. We cannot do this for other galaxies because they are too far away. So we get the light from all the stars together. So because we can measure how stars are moving, we can tell where they're coming from. Because we can measure how old they are, we can measure the age, we know when they were born, and from the chemical composition of the atmosphere, the elements that we can measure in the atmosphere of stars, we can tell about the environment in which such stars formed. And that's a wealth of information that actually allows us to put together the puzzle of how the galaxy was formed. So let me show you a movie of, this is a numerical simulation of how we think that galaxies are built through time. So what we think is after the Big Bang, small galaxies form first, and then they are pulled together through the mutual gravitational attraction. They merge, they produce larger and larger galaxies. They produce halos as they merge. You can see it's a very active history. At this point in time, this is roughly 3 billion years after the Big Bang. The age of the universe is 13.7, almost 14, so this is quite early in the use of a galaxy. And you can see that as galaxies are destroyed and they merge and they are destroyed, they actually leave behind these structures, right? They leave behind signatures that the stars were born actually in other systems. So we can tell that from the spatial distribution of the stars very far out. It's slightly more complicated, but not impossible to do if we look at the inner regions of these galaxies. So ideally, this movie is based on our current understanding of the universe, which is dominated by this cold dark matter, and with the idea that small galaxies form first. And so one of the things that we see happen in this movie very clearly is loads of mergers, right? So if you say, okay, is this theory correct? Is this model correct? Then one of the things you ought to find for the Milky Way is evidence that indeed it has experienced all of these mergers. And what's interesting is once you find the mergers, then you can ask, okay, how did these galaxies look like, in those early days when they actually merged? And so the idea is that if we look at the stellar halo, which is where all of these stars are deposited, we could identify the signatures of these mergers. We could find the stars that came on board these galaxies and reconstruct that history of the Milky Way. Now the question is, how do you do that? how do we find the leftovers of these mergers? So if we look at a simulation, and this is now the kind of the stars are color-coded, depending on in which galaxy they formed, you can see again that if you go very far out in the halo, you can sort of see substructures spatially that the colors cluster, right? So you could, if you map the distribution of stars at large distances, you could find the remains of different objects. But if you look in the inner regions, you see that it all overlaps. You saw that in the movie, the inner regions seem a mess. So how do we actually tell the different colors from one another? Now, the basic idea is shown in this movie. So if you take a small galaxy and you let it evolve, you see it disrupts, it forms these streams. And if you look at any given region of space, what you see is that the stars are moving together, right? They define these streams. So even if all of the stars at the end are sort of homogeneously distributed, in any given point in space, what you see are groups of stars that are moving together. They define these streams of stars moving through space, even if you didn't have, these two colors to distinguish the stars, you would still see that these are moving differently than the ones in the background. So that's the basic idea. So if I take a snapshot of this simulation, and I place myself, say, in the vicinity of the sun, and I look at the stars in this small box, then I would see stars that are moving up in this direction, and I would see stars moving up in that direction. So if I plot the velocities of the stars, then I have one clump corresponding to these stars, and a second clump corresponding to these stars. Right? So by looking at the motions, I can tell. There's one extra step, which is as you saw in the movie, initially all of the stars are together in the same location in space, and they're moving together through space. So if I measure the energy of those stars, and I measure their angular momentum, so how they move around the center, then all of the stars, they have very similar energy and angular momentum, so you get a clump in this space of energy and angular momentum. Now, it turns out that galactic systems are such that energy and angular momentum, these physical quantities, to a large extent don't change in time. So if initially they all had the same energy and angular momentum, at the end of the day, after the process is done, the merger process is done, they will also have very similar energy and very similar angular momentum. So what does it mean? It means that if I go back to this picture and I look at the velocities, I would find the clumps in the velocities from the different objects that merged. But I could also look in energy and angular momentum, and I would find for each one of the galaxies that merge, they would define a clump in this space. Yeah? So, and you can imagine that even if I didn't have this beautiful, rainbow of colors, if I have a clustering algorithm, an algorithm that identifies clumps, I should be able to identify all of these clumps, or some fraction of them. So we have a method. And this method I actually developed in my thesis in the year 2000, but the Gaia mission was only launched in 2013. So it took a while before we could put this to test. In fact, Gaia was launched in December 2013, and I want to share with you the actual launch.
3, 2, 1, top, décollage.
So at that time, I was on holidays in Argentina. It was around 6 a.m., the time of the launch, And all of the people, I think there's more than 500 people, had worked for the Gaia mission all of these years, from the year 2000 until launch. There's a lot that needs to happen before you get the satellite in space. And so you can imagine how nerve-wracking this moment is, right? You go. So it all went well. Gaia was launched, and it's been observing. It was placed on an orbit of about 1.5 million kilometers from the Earth, at a point that's stable dynamically, and from there it has been scanning the sky. It's in the same place where, for example, maybe some of you have heard of, the James Webb Telescope is currently observing, and the Euclid mission as well. So Gaia has been scanning the sky. It has done this for 10 years, and it measures basically the positions of the stars on the sky as with time. It also measures with photometers. It measures the flux that we can from the stars, and it also has a spectrometer from which we can measure, for example, the line of sight velocity or the velocity with respect to us. So one of the things we want is to measure the motions, right, of the stars on, basically, because we want to do this test of how the galaxy was formed. So how does this work? So if you take when the Earth moves around the sun and you look at a given star on the sky, if you look at the position of the star on the sky at different epochs, what you see is that it develops this ellipse when projected on the sky, and that ellipse, the size of that ellipse, depends on how distant the star is from us. Now, stars themselves move through space, so they don't only have this ellipse, but they have this motion that you'll see in a minute if I play this again. Sorry, I'll play this one more time. So that's the ellipse, which measures the parallax, or can be used to measure how distant the star is. But the stars themselves move. Everything moves if you have Gaia, actually. And they develop this kind of a motion, which reflects the intrinsic motion of the stars. So everything moves, which means to actually figure out how the stars are moving, it's quite a complicated mathematical problem. It requires loads of data. But that is what Gaia has been able to do. And to be able to measure, just to give you an idea of what kind of precision you need to be able to measure these motions of stars, Gaia is able to resolve to measure the size of a euro coin on the moon. This is what you need to actually be able to measure the motions of stars. So it's a very challenging thing to do, and that's why it takes a lot of time to develop a mission like this. I also wanted to give you a bit of context on why this has been such a revolutionary mission for us. So before Gaia was launched, the previous mission before Gaia was measuring the motions of stars, basically in a small region around the sun. Now with Gaia, we can basically probe the whole galaxy, so we can probe a volume that's 100,000 times bigger. We observe basically every object on the sky that's sufficiently bright, and we can measure it 100 times more precisely. And so all of these many factors of 10 actually lead to a revolution, have led to a revolution in the field. And just to make you a little bit dizzy with the numbers of objects that we have 2 billion stars. When Gaia was launched, I was watching another of these outreach videos. When it was launched, people said, oh, we'll measure a billion. It turns out there are 1.8 billion, so we were off by a factor 2. It's a large factor 2. So for these stars, we can measure their light, and from the light, we can infer temperatures, we can infer chemical compositions, we can infer also where they are, at what stage of evolution. Basically, Gaia observes everything on the sky that is sufficiently bright. And what that means is that there's a plethora of different science questions that you can answer, right? That you can address. And it goes from the scale of the solar system. So Gaia has been observing asteroids, and people have discovered there are different families of asteroids with different compositions. It measures how new stars are born near the sun and how they then evolve through space. We have found, we used to think that the Milky Way and galaxies in general were systems like universe islands in the sense of systems in isolation. We're seeing that that's not the case, and we have to review our modeling of such systems. We have been able to measure the distribution of dark matter around our galaxy, but also in nearby galaxies as well. And even the brightest quasar ever, very far away from us, was discovered thanks to Gaia. So every time I go to a conference and I talk about how excited I am about Gaia, I see people, fellow astronomers nodding, yeah, I've also used Gaia data for completely different things than what I was interested in, which is how did the Milky Way get to be this way? That's the question we're trying to address today. This is, in fact, the reason that Gaia was built, the main driver of the science. And so just to recap, remember small galaxies. This is, again, from a numerical simulation, a snapshot in the early universe. Small galaxies are formed first. They get together through gravity. They merge. They produce a stellar halo. And then in this system, a disk is born. That's the basic idea. So most of the stars in this disk were formed in our galaxy, but the stars in this halo were probably formed elsewhere. Or at least that is what we're trying to test. So now we have the motions, which is the fundamental tool to actually test this theory. And this is an animation of how the stars in our galaxy, this is no longer a simulation, this is based on real data. And as I was saying, basically everything moves once you can measure it, once you have such a wonderful instrument as Gaia. Okay, so what did we find? We have the motions. What did we find? So that's the amazing thing. So one of the first things we did was to plot, and this is again maybe a bit of a more complex diagram, but let me take you through it. What we did is make a graphic of the velocities of stars near the sun, right? We know we live in a disk galaxy. I told you stars in the disk move together very quietly. So most of the stars are moving like the sun. They are located here at roughly 230 kilometers a second around the galactic center. That's why you have such a high density of points. I can't plot every point is a star here, but here there are so many that I can't plot them all. And then as you move away from this very ordered motion, you get the stars that are in the halo, right? They have very big motions around the center of the galaxy. So basically, the stars beyond this red semicircle, they are in the halo. These are the halo stars. And one of the things we noticed when we first made this plot, which I think was the day after the data release of Gaia, the second data release, which was the one that's been so far really transformational, one thing we noticed is that basically there is a great number of stars that are here in this location that it's sort of the tail of this distribution, right? And then there is this clump here. And one of the things you notice is that this clump doesn't have, so most stars in the disk are moving clockwise, right? Like the clock, you see them here. These stars here seem to move preferentially slightly the opposite direction. So that's very peculiar and totally unexpected. And that was suspicious. But what turned out to be the case when we actually, so this is what we found. We found that the stars in the halo of fair fraction were moving the other way. When we looked at the chemical composition of the stars, we found that it was different, so different that we could tell these stars were not formed in the galaxy itself. So basically, half of the stars in the halo of the Milky Way did not form in the Milky Way itself. In fact, they formed in another galaxy. And because it was such a large number of stars, this was really a big merger that the Milky Way experienced. This is a numerical simulation of how we think that happened. We can tell when this happened from the ages of the stars. This was 10 billion years ago. Just for reference, the sun is 4.5. So this happened, in the youth of our galaxy. This object was really a milestone in the history of the Milky Way. It's the last big merger that the galaxy experienced. And as you can see from the movie, at the time, the galaxy had a disk, but that disk is really strongly perturbed. You cannot see these very ordered motions anymore. It's no longer thin. So in fact, this merger not only produced the stellar halo, but it also gave rise to this thick disk that I was talking about. So really a milestone in galactic history. And we gave it a name. We called it Gaia Enceladus. Gaia, of course, in honor of the mission, and Enceladus, because Enceladus is a giant in Greek mythology. So this was a relatively large, giant galaxy. It's the son of Gaia and the sky in Greek mythology, so that was very appropriate. And the myth says it's buried under Mount Etna, where it causes, earthquakes and shakes and so on. And so, indeed, Enceladus was buried in the Gaia data, was buried in the Milky Way, and has really caused some of the shaking that produced the thick disk. Okay, so we found the big fish. What about the other little fish? Is there other evidence of merger debris? So that requires a slightly more sophisticated method, which is looking at not just plotting the velocities of stars and finding that half of the stars are going the wrong way, but basically looking again at this space of energy and angular momentum and seeing if we can identify these clumps from the different objects that were accreted. So this is how the data looks like. This thing here is Gaia Enceladus. Are the stars associated to Gaia Enceladus? And you can by eye sort of see some clumps, right? But we do this properly, right? We developed a clustering algorithm. We assess the significance of features. And we identify several substructures, some large ones, like this one is called Sequoia. These are the streams that you were referring to early on, and quite a number of small clumps. What I find fascinating about this is that basically these stars were born in little galaxies, or some fraction of these, were born in little galaxies that merged with the Milky Way a long time ago. So we don't really need to go very far and observe very faint galaxies in the edges of the universe. We can actually figure out how galaxies at the early epochs in the universe were like by looking at stars in our own cosmic neighborhood. So these are the stars that built the early Milky Way, and that's why we refer to this field as archaeology, because from the present-day properties and the remains of objects, we reconstruct history. So what we're doing at the moment is we're trying to characterize each one of these clumps. So we're studying the properties of the stars to try to reconstruct the formation history, the star formation history. So we're asking, are these clumps associated to objects like this? These are star clusters where all of the stars are born at the same time. Or are they more like this, small dwarf galaxies? Or are they from big dwarf galaxies? That's kind of what we're trying to do. And by measuring the properties of stars, we can tell also how big these objects were and when they were accreted. So what we're trying to make it is family tree of the galaxy, right? We are here today. We found Gaia Enceladus. I'll have one that this is just a picture, but you get the idea, right? We're trying to find the ancestors of the Milky Way. In our search for leftovers, we actually found some surprises, and one of them is a black hole. Actually, Gaia can find black holes, because you might remember, if you have a single star moving through space, you have these ellipses, where the amplitude is proportional to the parallax, or how far the star is, and then you have a proper motion. But once a star is accompanied by another star, then it doesn't look so ordered anymore. And so you can actually tell that the star is not on its own, but it has a companion. And it turns out that one of these companions, the most recently found, is this Gaia BH3. So we see a star. This is the orbit of the star, and this is in the scale of the solar system. So we have Neptune here. If you try to find around which object this star is moving, then you find nothing. There's a black hole there, so no, it doesn't emit any light, and it's rather massive. It's 33 suns. And this is an interesting number. I don't know if you've been following the detection of gravitational waves. That's a hot topic in astronomy in recent years. And it turns out that these gravitational waves occur, for example, when two black holes merge. It turns out that the most often found mass of a black hole through gravitational waves is 33 solar masses. So that's a peculiar coincidence. Another coincidence is that this Gaia BH3 is actually part of one of the structures that we found that we could tell is this ED2 stream, that we could tell is a star cluster that was disrupted a long time ago. So we now know that at least black holes of 33 solar masses are born inside stellar clusters. We don't know whether it's a coincidence that it was born in such a cluster. It's also peculiar because this cluster is very pristine in terms of its chemical composition, so maybe there's a link there. But at least it helps us understand how such black holes are formed. So let me summarize where we are in terms of the timeline of the Milky Way. So we are here today. This is a depiction of our galaxy today. It's currently merging with a system that's called Sagittarius. It's almost completely destroyed, and with two other small systems that are the Magellanic Clouds. This is when the sun was born. This is the Big Bang, say, that's the timeline. Sun birth was here. Before that, we know now of this last major merger that the galaxy experienced in the youth, so it's a wild youth. And after that, not much happened. Of all these clumps that we have identified, we can place them in time. We have mice streams It's funny to say this. I feel always embarrassed about this. That were accreted something like 8 billion years ago, some other objects, but we really, one of the things, and then this ED2 object with its very massive black hole that formed really very early on in the universe. It's, as far as we can tell, it has the age of the universe. So it must have formed immediately, very, very quickly. One of the things you notice is around this period, we sort of know a lot, but going back further in time is not so easy, and the methods that we have their limitations. So what we need to do is we need to look at the next data releases from Gaia. So I say Gaia has observed for 10 years the sky. Actually, it has stopped observing after 10 years. It's now on an orbit around the sun. It was shut down. But the data it collected in those 10 years has not yet been analyzed. It needs to be put together in a database. We need to figure out which stars are really single stars, which stars are accompanied by other stars, by black holes, by planets. All of this information will come in the next year. So we expect a data release from Gaia at the end of next year and a final data release in 2030. And with that, the expectation is that we will be able to probe much further out in the galaxy, because the better the quality of the data, the further away you can then begin to explore and begin to address these questions. What is also happening is what we realize is that it's extremely important to understand the chemical composition of the stars, especially if you want to go back further in time. And so we've been constructing instruments on ground-based telescopes to actually measure spectra of stars, because with very high resolution, this is something that Gaia cannot do because of budget issues at the time we had to launch it. So on the ground, we can follow a number of these interesting stars. And if we have the chemical composition, the chemical DNA, we can tell where these stars were born. And that also allows us to deconstruct the different objects that fell in. So one of the instruments that has just seen the light about 3 weeks ago is on this telescope. It's called the Foremost instrument. This is in Chile, in Paranal, and it's currently observing the sky. It just started now taking data, so we're very excited about this. So what I wanted to, as a message to take along today, I guess today is not the best day to look at the night sky, but if you're lucky, maybe remember when you look up and you see that thin band of stars on the sky, it's so thin because the last major merger that the galaxy had was 10 billion years ago. And this is something that Gaia has told us. So Gaia has actually told us why the night sky looks the way it does. So thank you very much for your attention, and thank you also to my group and all of the people in the Gaia mission that have put together this amazing data set.
Thank you. Amina, thank you very, very much for your inspirational lecture, of course, fascinating, mind-blowing. I like you talking about giga years, I think.
Yes, billion years.
Billions of years. Right now we have half a minute, so that's very, very small compared to a giga year break. If you want to go to your lectures, you can do it now. There's now time for Q&A. So if you have any questions, please raise your hand and I will give you the mic. I think it's working. Go ahead.
Okay. Thank you very much. You told about black holes and the masses of a black hole, about an average of 33 masses of the sun.
Yes.
Is there a limit to the capacity of a black hole?
That's an interesting question.
Wow.
We don't know. we see black holes that are as massive as 10 to the 9 suns. 10 to the 9, that is 100 million, a billion suns. We actually see such very massive black holes. We don't know how to form such massive black holes. So that's why I think this, at least step, is interesting of identifying black holes that are not so low mass in the solar vicinity, because then maybe that gives us a handle on how to build up these very large ones. Yeah.
Incredible. And I'll come to you. Amina, the center of our Milky Way,
Yes.
hey, you explained that everything is moving
Moving around,
some
yes.
kind of center. What's in the center? Is there also a black hole
There
attracting?
is a very massive black hole in the center of the galaxy. That's about 1 million solar masses.
Okay.
But the reason, I mean, we move together because there's an extended mass distribution, right? So
Yes.
we all move together, say, around the center. We don't get very close to the center because we basically do a circle around it. So we never get very close.
Okay, but do you think in the end the black hole in the center will get bigger and stronger, heavier, consuming the whole Milky Way, or is that
No.
impossible? No, I'm just wondering.
Yeah, so the black hole our black hole is rather quiescent, and it does its stars in the environment. Every now and then it will kind of absorb the star or a gas cloud, and then it grows a little bit. But you need to get very close to the black hole to actually be swallowed by it.
I see.
And because most of the stars are in these circles, they never get very close to the black hole.
That's
So the only way, that's interesting, when you have mergers, then it's all very chaotic,
Yes.
right? And then you can get very large increase in mass of black holes.
yeah.
And black holes can merge too. So if each galaxy has a very massive black hole, then the black holes will merge as well.
Yes, yeah. Okay, but for now it's
We're safe,
reassuring.
we're
We're safe. I think the biggest danger is the growing of the sun, isn't it? I think that's the first thing swallowing the Earth, and then
Yes.
no, other things.
It will take a while though.
Luckily. So, go ahead.
Thank you very much. This was fascinating.
Thank you.
At the moment you introduced the conserved quantities, energy and angular momentum, I heard you say to a large extent conserved. So you left some provision there,
Yes.
and I'm interested, is there a measure of friction when these galaxies collide?
So gravity, there is friction, and that leads to some energy loss. But basically, the biggest reason why energy is not conserved is that the mass distribution varies a lot in time, actually. And the moment you have very large variations in time, energy is no longer a conserved quantity. But because the last merger happened such a long time ago, anything that basically after that, there were not very big changes in the overall distribution of stars in our galaxy, and therefore everything that fell in afterwards kind of follows this rule, which means that if you want to go further back in time, before this merger, you need a different way of looking at these clumps and trying to identify the different stars that came together on different systems. So the assumption works up to a certain extent and stage, and before that, we have to still figure out what is the optimal way. Yes.
Yeah, okay.
Very good question.
Thank you. Are there any more questions?
Yes, thank you. I would like to ask you, I think that I may say that the halo stars are dark, so that they might be something like the dark matter. And is then there also something to say about the halos, including the black holes, that they are both responsible for all the dark matter we still miss in the universe?
Yeah, so
Interesting. Thank you.
halo stars are normal stars. So they are not particularly faint or dark. They are faint because they are farther away, but intrinsically there's nothing peculiar about this. But we have the halo of dark matter. And so you can ask, could there be dark stars in there? And it turns out we've looked for such stars that we can put upper limits. There's no dark stars as far as we can tell. Yeah, and so it's still an open question of what dark matter is. What we think it is most likely is fundamental particles that we still have to detect. So it's an big open question, because there's more dark matter, 6 times more dark matter than normal matter in the universe. So it's a headache.
But it couldn't be just dust instead of fundamental particles?
No, there are different ways of looking at this, but one of the ways is if we look at the radiation left over from the Big Bang, that's the cosmic microwave background. You can measure how much mass was there at the time and the fluctuations in the density, and it's not enough in terms of that radiation and how much normal matter was present in the universe at that time. You need more matter to explain what you see today. So we know it's not normal matter.
Interesting. Okay, next question.
Thank you. We all see all these pictures from light, what is centered billions of years ago. Have you any idea how the position would be of these stars, or what has happened in the actual time now?
Yeah, interesting. Yeah, I mean, you can, because in fact, one of the movies I showed were with the Milky Way and all of the stars moving. Actually, what we measure is we measure the position, indeed, at the moment they emitted the light, but we also measure how they are moving. So if we have a good model for the distribution for the force field, then we can tell where the star will be, say, 10 million years into the future, or 10 million years into the past, or whatever time scale you wish. So we can tell where they were. And there's nothing, so that's an interesting way of looking at, especially near the sun, at looking at stars that were born together, like in a star cluster, and what sees them spreading out today. So one way of identifying where they were born is kind of to play the movie backwards and find that they come from the same place. The reason you see a lot of activity, I didn't spend time on this in the movie, is that the universe a long time ago was smaller. So it was denser, and so you had more chances of colliding with other systems. Now it's expanding, and therefore the distance between galaxies becomes bigger, and so mergers become rarer. But the Milky Way will merge with its biggest neighbor, the Andromeda galaxy, in about, I would say, 5 billion years, 5 giga-years. This is also around the time we will be swallowed by the sun. So it happens on the same time scale. And it's also around the time it merges with the Magellanic Clouds, which are falling in now for the first time. So the interesting thing is that indeed, I mean, except being swallowed by the sun in principle, we will not notice anything about these mergers, except that when two galaxies get together, And if they have a lot of gas, then you can form very many stars in one go, and that's called a starburst. And so you see lots of supernovae, so massive stars exploding. So the sky would be full of this kind of shining lights. And the distribution of stars, if we were able to be there, would no longer be this disk, but we would see stars everywhere on the sky. We would no longer see the Milky Way as a band.
Yes. Cool.
Yeah.
But then we have to move to Mars first, I think. Is that
There's
safe?
no, it will look the same.
Oh, is there still, how big is the sun going to be?
Yeah, the sun it will get a lot bigger. I think it goes, I don't remember this exactly, but it's beyond the orbit of Mars.
Oh, wow.
Yeah.
But we have some time.
There's some time. I mean, that depends. So whenever you look into the future, you're making a prediction, right? And so that depends on our level of understanding. The measurements are there, so Gaia measures. This is the measurement. And then our interpretation of what it means for the future depends on how good our models and understanding is. So on the basis of that, there is this idea that the Milky Way will merge with Andromeda. We don't know exactly. There's some debate actually at the moment because apparently the dynamics is slightly more complex than what we thought. So we're trying to, there are some people that say there's a 50% chance that we will not merge with Andromeda. I think that's a bit too extreme, but it, as this shows, it depends a lot on our understanding, and so it's a continuous field that's developing. Yes, it's a stationary point. So whenever you have, so what we have is the sun and the Earth, say to first order, and if you you take a third object, say a satellite, depending on where it is and the velocity of the object, it can be in a location where it's stationary. So it always sees this. It always has the sun at the same distance and the Earth at the same distance. And this triangle moves together through time and maintains the shape. So it's a very stable, in that context position. It's a Lagrangian point, yes, like you say. And so we like putting objects there because it's stable, it doesn't cost energy, so we can keep them there. Once they are there, they stay there, unless you give it a kick.
Yeah.
And so that's where we put also the Planck mission, James Webb, the Euclid, and it's becoming more and more crowded because we like it there. And so Gaia, when it was shut down, it was giving a little kick such that it would move away. And so now it's moving on its own around the sun. And it will come back close to the Earth in about 11 years. Yeah. But now there's more space for other missions.
Yes. I see. Fascinating. It's a nice combination of...
Yes, interesting question. Yeah, so there is a project in the making that's called Gaia Near. And the idea, it's not yet been adopted by the ESA, the European Space Agency, but the idea would be that it would be launched in 2040, if one is lucky. So it's going to take a while. And the difference with Gaia observes in the visual, and Gaia Near would observe in the near infrared, so it can pierce through dust. So you saw some of the images, you can see those dark regions, they're just dust clouds, but behind the clouds, there are stars, and we cannot see them. So it would allow us to go much closer to the central regions of the galaxy and understand much better the dynamics of the disk, and find many more exoplanets. And
I was wondering, Gaia produced lots of data, and you explained very clearly that, I think, which part of it is already analyzed?
It's now, of the 10 years, it's 5 years we've analyzed.
Wow, okay. And I was wondering, are you using AI models to analyze the data? Because you read a lot
Yeah,
of
yeah.
AI, and I think it's all about pattern recognition.
Yes.
Do you use those kind of
Definitely, yeah. We do, especially as more and more data comes, and the obvious things we have done. So then you really want to exploit AI, data mining tools, and so on. Yeah.
I think that sounds really
Yes. Yeah.
good
It's
combination.
indeed.
See
Yes.
those two.
Yeah.
I have one more speculative question. I'm not sure if you can answer it, but many of us are very curious, of course, if there is life on other planets. You have all these wonderful instruments. In the beginning, you showed other planets which are not
Yes.
in our solar system, but elsewhere.
Yes.
Do you? I think you ask yourself the question. But can you say something about this, or not yet?
Not yet.
Yeah, right?
So we are building instruments because what you want is basically to be able to image a planet and to measure, and particularly to obtain spectra of a planet, to look for the indications, and this is what are possible indications of life. And there is a big question about what would be possible indications of life, and also life would be, what I call life is something very broad, right? It can be, I don't know, microorganisms, whatever, but some activity that would tell you that the planet is not dead. And so sometimes signatures like if there's ozone, there are some spectral signatures that could be indicative of life, but the issue is because a planet orbits around a star, you need the starlight also for life.
Yes, yeah.
And the star is so much brighter than the planet. This is very challenging.
Yes, how do you, because there's so much interference
From the star itself.
And from the star itself, but also from other stars.
Yeah, but it's mostly the killer is the star itself. Because the planet, if it's very far, will be very close to the star, and so will be surrounded by that starlight. And so there are people developing, or very large teams developing techniques to suppress the starlight, to see the planet and then to measure its properties. And the expectation is we're beginning to do this. And also closer planets are easier to characterize. So maybe beginning of the next decade, at least the ones in our immediate vicinity, we may get some insights on whether there is, at least of the planets themselves. I'm not sure life, because that would be a big question. But those signatures, that's what we're after, indications of what people in the field call non-equilibrium chemistry.
Yes,
So
non-equilibrium, that can
produced by some process that doesn't happen naturally.
And molecules which can reproduce themselves or something like that.
Yeah.
Wow, very, very cool. One final question, and then we have to round off. No, you're all processing the information. Yes. Oh, two questions. I think we can do it. Let me see. You were first.
So in the table where you showed how the galaxy of the stars are moving through the galaxy, a lot of them are moving at 230 kilometers an hour clockwise.
Yes.
But for counterclockwise, a lot of them, or there were exceptions which moved a lot faster. Why is this for counterclockwise and not for clockwise?
Yeah, that's a very interesting question. So it turns out, if you say, because we rotate at 230 around the galactic center, if you say what is at rest with respect to the center of the galaxy, that is at 0. So you could have stars here moving fast. Now, it turns out that these stars here actually are stars from, a fair fraction of these are stars from Gaia Enceladus, from the object, but that fell in, that were lost very early on. So they have very, very large velocities, which brings them very far out in the galaxy. So these are the first stars that were lost, and they are on the negative side, because actually when Gaia Enceladus fell in, it was going counterclockwise. And so that's why it deposited stars here rather than here. And there is an indication indeed that kind of if you go further out in the galaxy, then there are more and more stars that have these negative velocities, which would indicate that kind of these objects all came from this direction. This, we don't know what produces that. This is how it is for our galaxy. We'll have to figure out if this is common. We're trying to develop models to understand whether this is a common signature, if it has something to do with the environment in which we live, or is something peculiar for the Milky Way.
Amina Helmi, I want to thank you. I have one more question. Is it possible on a very, very dark place on Earth to watch the Milky Way and see the Helmi stream?
No.
I was
unfortunately not. No.
Why not? Is it too tiny, or what's the problem?
The stars are too far. And so that makes them fainter, and so they cannot be seen with the naked eye.
Okay.
Unfortunately.
Okay. No.
Yeah.
No problem, but you can see it on the beautiful animations. Amina Helmi, I want to thank you very, very much for your inspirational lecture. Thank you very much.
Thank you.
Thank you. Great.